It's going to be that easy for the rest of the time, of course. That's how easy limits. No, it always gets more complicated. But down below, there's all these rules about limits. They really just get, this is the shortcut to all these rules right here, is that a limit travels to where it's needed. So the limit as x goes to -7 applies to wherever there's an x in your algebraic expression. So all these little things here are me writing the limit wherever the x is in the function. So it travels where it's needed. If you can remember that, then you don't even have to look at that rule set. Just say the limit travels where it's needed. It's very useful. You know, you just go where you're needed. So on this page, I think, now for a long time, AP Calculus has a pretty good list of things that you're supposed to memorize, and this was one of them. The limit as x approaches 0 of sine of x equals over x equals 1. I don't believe it. I want it proven. That should be your standard procedure. You should be skeptical. Just be skeptical. Okay? That's good advice. And be grumpy. Skeptical and grumpy. They're a good combination. Or maybe you should wait till you're in your 70s before you do that. But okay, so now this graph right here, would you guys agree? Here's sine of x over x. Does it look like as x approaches 0 from both sides? Here I am coming in from the left, from the right. It looks like it's going to 1. So that's why in calculus they say memorize it so that you don't have to graph this every time. You can't direct substitute because there's a hole right there, just like we'd expect, because it causes division by a 0. But you also cannot cancel. This is not one you can factor and cancel. That happens sometimes. And so they just leave that as, hey, just know this one. Now, there is this cool technique called L'Hopital's rule for evaluating limits. And it used to be a Calc 2 topic, so there's a way to evaluate this is equal to 1, like prove it. I think they have to do it in Calc 1 now too, so maybe they don't. But it is true, it's equal to 1, and there is a technique for doing it algebraically. But let's just say we know it. And that's why it says given, find the following limit. Just imagine that you looked at the graph and it was like this little hill mounded up here, and it went to a height of 1. Okay. Now this is what that limit algebra was on that previous page. It says, do all the algebra you want with the expression you have. Now, don't lose all your algebra chops. Look at this. Remember that? If you're dividing two numbers by x, you can split it. That's a thing. The limit, oopsie. The limit as x approaches 0. Do your algebra stuff. Make it x over x and sine of x over x. Because you can, and you know it's a good thing. And hey, x over x cancels. That's cool. I mean, that happened. See that? Cancels. So that just ends up being 1. So now it's the limit as x goes to 0 of 1 plus sine x over x. Now limits, like I said, travel where they're needed. It goes to anywhere there's an x expression, you just move that over there and evaluate it. Now the 1 does not have an x in it. It's just 1. So the limit does not affect it at all. So this can be rewritten according to the rules on the previous page. You can just move that limit right on over. You can snuggle it up against the function that actually has x's in it, because that'd be nice. And either you use L'Hopital's rule, because you're off and running and you're a superstar, or you just use the given up there that says, hey, the limit as x goes to 0, sine of x over x is 1, and I saw the graph and I know it's true. Ooh, 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 I love you, limits. Do you know what song that is? Girl, you know it's true. Ooh, ooh. No, okay. It was a long time ago. This is 1. That means I just got 1 plus 1 is 2. So limits have a value. So remember when I said guess at the beginning of your work, I said you have an answer that is either, I want you to write down a number, or does not exist for your limit. It's not going to be infinity in these. Limits have a value. Sometimes it is infinity, but for most of these, it's what we call like a convergent or an actual value. So the limit of the original thing is 2. The way I did it was I did a little algebra, split it up. Oh, made my x's cancel. We love when stuff cancels in limits. The limit applies to things that have x's in it, so I moved it next to the xy stuff. And then I evaluated this limit either by graphing it or somebody tells me it's equal to 1, which we did. So it's just 1. 1 plus 1 is 2. Isn't that cool? So algebra is actually all of limits is just a whole lot of algebra. So we continue. What about 1 minus cosine squared? Do you have that, like, do you hear that ringing going off? That beep beep? You hear that? It's your PIDDAR going off. So, isn't it awesome how I had that time just right? I called down there and I said, will you guys make the bell ring a little earlier today so it goes off during my notes? Man, it's awesome to have power. Maybe that's what it's all about. Leadership is about power. That should go to our discussion. Leadership. Okay, we'll get back to that topic later because I am recording. So this is sine squared. Some people think it is. It's a good topic. So sine squared over x squared. You okay with that? It's PID. Remember the alarm went off, meaning PIDDAR, PIDDAR. That is an expression that you guys know. Do you remember that when you square sine, it's actually like sine of x, the whole shebang squared? Oh yeah, now you remember it. Oh, do you remember that when the numerator and denominator are both squared? Do you remember that rule that if you square a fraction, you actually square the top and the bottom? Well, the reverse of that is this. I want you guys to look at all the stuff that we've learned and the fact that we have to keep using it. Isn't that cool? No comment. It is cool. I heard that. What do you think about that? Ponder it for a second. But if you have a fraction and both parts have the same exponent, squared and squared, that power can be applied to them both. You can actually extract it. The power of a fraction you distribute to the top and the bottom, and then the reverse is also true. Cool. Do you guys see what's inside there? Do you see that this limit, remember how useful they are? They're so cool. They actually travel where they're needed. They're willing to jump inside the parentheses with that sign of x over x and be squared with it. That says a lot about limits. They're very generous in general. They go where they're needed. The limit as x goes to 0. It's going to just snuggle in there with its sign of x over x. It's so cute. And then it's going to get squared. But it goes where it's needed, where the x's are. Now this is the one we know. Sign of x over x, limit as x goes to 0. It's totally 1. This is 1. That means we win. 1 squared is 1. That limit is 1. But that's the cool algebra. Limit goes where it's needed. The rest is just algebra rules. All right. That brings us to what's called limits at infinity. We're going to talk about end behavior in a minute.